Welcome friends, Igor is here, and in this video we will discover connections between the kernel of a linear transformation and the null space of its matrix representation. In this lesson we will prove that the kernel of a linear transformation is isomorphic to the null space of its matrix representation, and we will use this isomorphism to compute the kernel of one linear transformation. Let's get started. Suppose we have a linear transformation T that goes from a vector space U to a vector space V. We choose any basis B for the vector space U and any basis C for the vector space V. This allows us to construct the matrix representation of the linear transformation T relative to these two bases. And I claim that the kernel of the linear transformation as a vector space is isomorphic to the null space of the matrix representation. Vector spaces are isomorphic when there is an invertible linear transformation between them. So to prove that the kernel is isomorphic to the null space, we need to construct an invertible linear transformation that goes from the kernel to the null space. The kernel of T is a subspace of the domain U, and the null space of the matrix representation is a subspace of Cn, where n is the dimension of the domain U. This is because this matrix representation has n columns. Here is an idea for the proof. We already have an isomorphism from U to Cn. This isomorphism is given by the vector representation relative to the basis B. To construct an isomorphism from kernel to the null space, we will simply take the restriction of this function rho B. Here is a picture to help you see what is going on. The big outer square describes the fundamental theorem of matrix representation that we discussed in the last video. Notice this vector representation isomorphism rho B that goes from the vector space U down to Cn. Also, the kernel of T is a subspace of U, and the null space of the matrix representation is a subspace of Cn. To establish an isomorphism between these two subspaces, we will consider the restriction of rho B to the subspace kernel of T. First, let's make sure that the restriction of rho B to the kernel becomes a function into the null space. In other words, we need to make sure that all elements of the kernel of T are sent to the elements of the null space of the matrix representation by rho B. So let's take any vector U in the kernel of T. Then we are going to look at the following matrix vector product. We apply the fundamental theorem of matrix representation to the linear transformation T, and T of U is the zero vector because U comes from the kernel of T. Also, the vector representation rho C as a linear transformation sends zero vector to the zero vector. This shows that the matrix representation multiplies the vector rho B of U to the zero vector, and this is exactly what it means for this vector to be a member of the null space of the matrix. This establishes that the restriction of rho B to the kernel of T becomes a linear transformation from the kernel to the null space. And now all that remains for us to do is to show that this linear transformation is invertible. It is automatically injective because it is a restriction of rho B, and we already know that rho B is an injective linear transformation. So the only question here is why this restriction is surjective. Let's take any vector in the codomain of this linear transformation, so it's a vector x from the null space of the matrix representation. Also, let vector U be the uncoordinatization of the vector x. This is a vector in the vector space U. Let's check that this vector U in fact is a member of the kernel of T. For this, we will show that the value of T on the vector U is the zero vector. Let's recall that the vector U was constructed as rho B inverse applied to the vector x. Now, let's apply the fundamental theorem of matrix representation to the linear transformation T. Notice that we have rho B and rho B inverse in the middle. They compose to the identity linear transformation because they are inverses of each other. And of course, the identity linear transformation does not change its input. We chose the vector x as a member of the null space of the matrix representation, therefore this matrix multiplies the vector x to the zero vector. And uncoordinatizing a zero vector is the zero vector. Why? For example, rho C inverse is a linear transformation, so it sends 0 vector to the 0 vector. This shows that T of u is the 0 vector, and therefore we verified that u is a vector in the kernel of T. Also, because the vector u was uncoordinatization of the vector x, rho b of u is the vector x. So here's what we achieved. We took an arbitrary vector x in the null space, and we showed that this vector x is equal to the value of rho b on an element of the kernel of T. This is saying precisely that the restriction of rho b to the kernel is surjective as a linear transformation from the kernel to the null space. So this restriction is both injective and surjective, therefore it is invertible. We have constructed an invertible linear transformation between these two subspaces, and therefore they are indeed isomorphic. Here's an example of how this result can be used in practice. Let's compute the kernel of this linear transformation from the vector space of 2 by 3 matrices into the vector space of polynomials of degree at most 3. To construct a matrix representation of this linear transformation, we need to fix a basis B of the domain and the basis C of the codomain. We are free to choose any basis, so we are going to choose a nice basis for the vector space of matrices and a nice basis for the vector space of polynomials. We will compute the matrix representation of T relative to the bases B and C using its column-by-column definition. The first column of this matrix is given as a value of rho C on T applied to the first vector in the basis B. We have a formula for T, so we can compute this value, and we can coordinatize this polynomial relative to the basis C. The second column of this matrix is the value of rho C on T applied to the second vector in the basis B. We know what T does to any matrix, and we can easily coordinatize this polynomial relative to the nice basis C. We then compute the third column of the matrix by using the third vector in the basis B. We compute the value of T, and then we coordinatize relative to the basis C. We do the same for the fourth vector in the basis. We compute the value of T. We coordinatize this relative to the basis C. Then the fifth column, which corresponds to the fifth vector in the basis B, compute the value of T, coordinatize relative to C, and finally the sixth column, we take the sixth vector in the basis B, compute the value of T, and then coordinatize this polynomial relative to the basis C. We have computed all 6 columns of the matrix representation, therefore this is what the matrix looks like. Next, let's compute the null space of this matrix, and this is a task which we know how to complete. We find the reduced row echelon form of this matrix, and we notice that there are 2 non-pivot columns, column 4 and column 6. They correspond to the variables D and F. Then we apply our standard technique to find a basis for the null space of this matrix. There are 2 non-pivot columns in the reduced matrix, therefore there are 2 vectors in the basis of the null space. But now we are going to use this basis of the null space to construct the basis of the kernel of the linear transformation. The kernel of T is isomorphic to the null space of the matrix representation via the vector representation function rho b. So, to go from the null space back to the kernel, we simply have to apply the inverse of rho b. In other words, we uncoordinatize the vectors relative to the basis B. This tells us that the kernel of T has these 2 matrices as a basis. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will prove that the range of a linear transformation is isomorphic to the column space of its matrix representation. I will see you later.